We'll give another minute for people to join.
Sure. I seems like I'm unable to start my video.
Oh, okay, that's fine. So since you have the presentation, that's fine.
Okay.
Okay, we'll start. Well, I welcome everyone once again to PyCon 2023 Sri Lanka. I am delighted to introduce our next speaker, Dulaj Disanayaka, who will be presenting a session titled Optimization of Mere Models. In this session, Dulaj will explore the importance of code optimization in the context of limited resources and real-world implications. He will specifically focus on micro optimization and share valuable insights on developing good coding habits to avoid them in the future. To brief you guys about speaker, Dulaj Disanayaka is a seasoned software engineer with a wealth of experience in development, architecture, and project management. With an MSc in data science, he possesses extensive knowledge in high-performance computing and functional backend development in Python. Currently working as a software engineer at Skits, Netherlands, Dulaj's primary focus lies in architecting and developing Python backends. We are fortunate to have Dulaj with us today to share his expertise in code optimization and offer practical advice on writing non-angelic code that performs well without sacrificing developer time. So without further ado, please join me welcoming Dulaj Disanayaka to the stage. Take it away, Dulaj.
Thanks, Asil. Seems like I can't share my video, so let me share my screen right away.
Yes.
Yeah, hope everyone can see it. So, okay, to start off, some people really like optimizations and the rest of us really hate thinking about or doing optimizations in our code base. Today, I will try to bring everyone more or less to the same ground regarding discussing and applying optimizations. So who am I? My name is Dulaj Disanayaka, as Ashid mentioned. I'm an engineer at STEX. I have a master's in data science and a BSc in computer science. I'm 31 years old. Yeah, I do photography here and there in my free time. And I moved to Netherlands in last October. So before everything, let me lay out some things that I won't be talking about in terms of optimizations. I won't be talking about the fact that Python is really slow. It's 100% true. If you use a compiled language like C++ or Rust, you would know how slow Python is. That snail's name is Gil, by the way. With recent versions of Python, it has become reasonably faster, especially since Python 3.11. But more importantly, speed is not everything that we are looking for in a programming language. For example, the readability, maintainability, huge community around the language, and third-party libraries is unmatchable by any other language comparing to Python, actually. Also, I won't be talking about switching your interpreter to a different one from CPython, and also compiling your Python code as well. These are actually some legitimate methods of gaining higher performance, but it would take another discussion to get through everything regarding these aspects. So I won't be focusing on that today as well. So let's talk about optimizations. We currently are living in a world that we have seemingly unlimited amount of hardware resources. We don't need to decide between an 8-bit integer versus 32-bit integer and count bytes when you are developing software solutions anymore. And because of that, nowadays we have a little bit of stigma around talking about and applying optimization. It's mostly created by high-level language communities like ourselves, but it's actually there. So here are some most commonly thrown around phrases that we hear. First one is premature optimization is bad. The second one is a little bit uncommon, but the second one is micro optimization is bad. So let's try to break this down a bit. So if you know, Donald Knuth once famously said premature optimization is the root of all evil. He also, in the same sentence, said that not to worry about optimization in the wrong place at the wrong time. So what's the wrong time and what exactly is premature? So thinking about optimizations right before you have written any line of code is obviously too soon. And thinking about optimizations when you had a huge issue in your production system and you lost millions of dollars is too late. So somewhere in between is the correct time actually. And also, so this premature optimization is bad phrase is a little bit too vague. So let's try to correct that a little bit. So basically why premature optimization is bad is because you can spend time on feature development and bug fixes, which would give you higher ROI. There will come a time that you will have to spend significant amount of developer time in optimizations, comparing to feature development and bug fixes, but when that is actually judgment call. So let's move on to the next argument, which is that micro optimization is bad. So why do we consider micro optimization bad? The reason is if you have a non-optimal system and so if you have an non-optimal system, you can actually spend a very little time doing macro optimization, which will give you higher return on investment rather than going through your code and trying to do some small micro optimizations. But the issue is every code segment in your code base is not actually treated equally. For example, there can be some parts of your system that's utilized millions of times more than other part of your system. So micro optimization bad is not actually correct phrase. I think the correct wording of this is that code optimization is bad, not all micro optimization is bad. Again, comparing between macro optimizations and micro optimizations, as well as comparing between micro optimizations and call path optimizations, we also we are talking about return on investment on the time spent on our code base doing optimization. So we are coming back to this return on investment term every time we discuss about optimizations. Optimization is actually a meta problem. When, where, and how you allocate your resources or developer time doing optimizations does actually matter. So you have to optimize the time you spend on doing optimizations. So we have this contention between feature development and bug fixes on the one hand, and on the other hand, we have code quality improvements, code cleanups, and optimization. So you have to decide between the two of them. But There's actually a third way of looking at this, where you can actually develop features and do bug fixes, all the while keeping your code smooth and in an acceptable level in terms of performance. So the solution actually is opportunistic optimizations. This is completely made up term by me, just so we have a common wording to discuss this this idea. So opportunistic optimization is a combination between premature optimization and micro optimization. So one level above the root of all evil. It's but more importantly, it's not about going through your code base with a magnifying glass and trying to improve things like we do in micro optimizations. It's more like if you know Boy Scout rule, but more specifically for optimizations, basically making the code a little bit better than you found it. This last point is really important. You are not pressured to always improve your code base when you touch it, because that's actually impossible. This should be a really passive thing that you do when you are doing feature development or working on something on your regular work. So again, the idea is to passively keep an eye out for simple improvements that you can do on your code base. And these simple improvements has to amount for significant performance improvements, at least in the context that you are working on. Lastly, it's not actually a strict set of guidelines that you need to follow. It's a mindset that you should develop as a developer. To simplify things, the basic idea is to make that phase when you see a suspicious code segment, either that you are writing or that you are reviewing. So how do you develop this mindset or mentality? There are two things or two traits that you need to master. First one is to keep an abstract idea about the whole code base that you are working on, or at least the subsection that you are working on, and performance implications that certain decisions has on your code base. The second thing is to deeply understand and know your tech stack, and and be able to apply specific features in your tech stack to overcome those performance implications. It's not necessary to know every nook and cranny of the tech stack, but at least know how you can find answers once you know the problems. So there are a few points that you need to keep in mind while applying this principle. First of all, again, you are not compelled to improve your code always, because most of the time, especially if you are applying opportunistic optimizations day-to-day regularly, you won't be able to improve your code base always. The second point is you should only do micro optimizations. The focus here is to do quick changes that would amount for significant performance improvements. The third point is really important. If you know your tech stack really well, you will know some weird ways you can squeeze out performance out of it. Just don't do it. I'm sorry. Just don't do it. The hacks that you will apply today will be fixed in the future by the framework or the language, and you will be left with some very confusing and most probably non-optimal code segments in your code base. The last point is never to compromise readability in favor of performance unless you have a very, very good reason not to do that. So if you, not sure if you are aware, but there's a very famous square root function in Quake 3, which is really unreadable, but the requirement for that function is to have higher performance than a regular square root function. If the stakes are that high, you can bend the rules a little bit, but most of the time you won't need to, and try not to as well. So that's basically is the idea. It's not that complicated, but let's go through some example to really understand what I mean by opportunistic optimization. So this first example is regarding Python inbuilts. You have to understand that operations in Python and Python language as a whole is really, really slow. But inbuilts in Python are written in inbuilts in Python in a standard library, and most operations in Python are written in low-level C, which are really fast. So when you write code, try to push things as much as possible to inbuilt functions or language features in Python. So let's go through this code base. Code segment. First of all, you can see from line 2 to 13, first of all, we are getting three lists of lists as arguments, and we are trying to clear out none and empty values out of these lists. There are actually better ways of doing that, but let's move on. Secondly, we are trying to get all combinations of wine, cheese, and meat. And also we need an index over these iterations. So we are trying to increment an index in each iteration. I need to point something out here. For ranges in Python is actually 50% faster than while loops in Python, just because for loops doesn't have to do this increment in Python side. It's done in low-level C side. So if we can avoid these kind of increments, we should do that. And in line 19 and 24, we see a huge problem. We are calling this get parent score function twice in each iteration. Once on the if clause, and again to print the score as well, which is not optimal. We can do better. Print statement here, we are trying to concatenate some strings to format it. There also are better ways to do that. So remember, we need to make that face if you see these kind of code segments. So yeah, first problem can be solved by list comprehension. The second problems can be solved with some utility functions. And we can use f strings, walrus operator to fix this issue. So let's try to fix it. First of all, we have used generator comprehension to clean out all the unnecessary data from the list, and to get all combinations of multiple lists, we can use iterative product function. And on top of that, since we need an incremental index as well, we are using enumerate function to get that. If you want to get, bind substatements result to a variable, you can use walrus operator. Here I have used this, I have bound parent score variable to the get parent score result. So I can use that on if statement as well as inside the scope as well. You can use f strings to format strings. You don't have to use string concatenation to do that. One thing I have to mention here is that there are some security concerns with f strings using in the context of with string formatting actually. So it's not a good idea to use f strings in logger module, for example, in Python, but just be aware of that issue, and you can find exactly what I mean in more details online. So this looks good now. Let's move on. So this next example is about data structures in Python. We see that we have a class called coordinates to store two XY coordinates. And we have NPC coordinates list, which contains some coordinates. And also note that we, so for the sake of this argument, let's assume the number of NPCs is constant. And right below, we are trying to get unique coordinates going through the list and trying to just to get anything that's not repeated. So first of all, we don't have to use this kind of very generic, very slow class just to store these XY coordinates. And second of all, we are using a list to store some constant length data set, which we don't have to do that. And also, at last, we can use, there are better ways that we can get unique set out of a list rather than going through everything and calculating everything ourselves. So let's try to fix this again. First of all, we can use a data class for coordinates. And note that I have used slots equals true, which is, I think, a Python 3.10 feature. Which will allow you to have which will allow you to define slots in coordinates. Basically, what it will do is you won't be able to dynamically add variables or class level variables to coordinates anymore, which is completely fine. And since I will be using this coordinates class in a set, I have defined dunder hash function as well. NPC coordinates, since it's constant, we can use a tuple. And finally, to get a unique set of coordinates, drop in any duplicates, we can use a set. Here, since we have constant list, I have used a frozen set, which is a constant length set actually. So frozen set is not more optimal than a regular set, but it's good to be descriptive than to let the interpreter assume. So let's move on to the other example. This is regarding object lifecycle in Python. So first of all, we have this email utility function, which contains some, email utility class, which contains some functions, which will allow you to manipulate and reason about emails. First, we have this isValid email function, which will return if an email matches a regex or not. One thing immediately that's noticeable here is that in isValid email function, we are not using self object. So the scope seems wrong because we don't need this to be inside the email utility object itself. Also, inside isValid email, there's a little bit, also a bit of a performance issue. We compile this regex every time this function is called, which is also not a good idea. So moving on, in email exists function, we see that we are getting Boolean out if the given email is inside this emails list. One thing to notice here is that emails is actually a private variable and it's not changed in the lifespan of this object because it's not exposed. So this email exists output is actually constant throughout the lifespan of this object. So the output can be cached in this case. Email counts, similarly, it's constant, so it should be cached on each email count call. Moving on, we have this get whitelisted emails function, which will get a checker function and a limit, and it will return a list of emails that pass this checker, and it will limit the output to the given limit. Again, we are seeing a problem here. We are evaluating all emails in this private emails list just to get a very small amount of subset out of that. So doesn't look that good as well. So let's try to fix this. First of all, isValid email can be a static method because we are not using the self object. And more importantly, the regex should not be created every time that we call that function. So here I have assigned that regex to the function object and reused it. Might be a little bit controversial, but if you don't like this kind of code, and if you think it's not readable, you can always keep that regex in an object and initialize it in done the init method, or you can have it as a class variable as well. Email exists, as I mentioned, can be cached, so we can use functools cache decorator for that. And email count is not getting any input parameter, so it can be a cached property actually, depending on your preference. But cache property is a little bit performance favored than using cache. Get whitelisted emails is obviously should be an iterator because we shouldn't calculate everything just to get a small subset of subset from the list. So we are using this filter function given a list and a checker and a filter function. Will return you an iterator over that list that will only the items that will only pass that filter function. We use islice function over that filtered generator just to get the first items from that generator according to the limit that's given. So again, this looks good. There are other methods of improving your code base using third-party libraries as well. These third-party libraries, for example, pandas, numpy, scipy, matplotlib, tensorflow, everything is written in low-level C, so they are really good in performance. I have mentioned here an example in NumPy, how the array is formatted in NumPy actually. If you take a look at Python lists, first of all, there are two levels of indirections in Python lists. When you want to get an item out of Python lists, you have to go to, you have to get the the memory location of that object, and you have to access that object. Two indirection is not that optimal, and also the main problem is that all the objects are scattered throughout the memory, so you don't get any hardware level caching as well. So Python lists are really inefficient. Comparing that to NumPy arrays are stored as a contiguous chunk in the memory, and it's accessible through one indirection. Because of that, it's really fast, and you will get hardware level caching as well. So this is only one example, but for example, if you use pandas library for data manipulations, you will get hugely good performance improvements rather than using simple Python based solution. It's not possible to go through everything that's available via third-party libraries. So I will be giving you the opportunity to use any third-party library that's needed or available in your context. The basic idea is to know the mindset of opportunistic optimizations rather than to go through every example that's possible, basically. There are a few things I also didn't mention. First of all, Python 3.10 introduced match statements. If you're coming from any other language like C++ or Java, you might have used switch statements, which are extremely faster than if having a list of if-else statements, because switch statements are using jump tables. And you might be thinking match statements are something similar, but it's actually not. So match statements, how Python has implemented match statements is that it's more or less completely similar to having a list of if-else statements. It's readability thing rather than a performance optimization thing. So it's really good idea to use match statements to make your code more readable, but it's you won't get any performance improvements out of that. I didn't mention multi-threading also. First of all, going through multi-threading, multi-processing, or async IO kind of solution, you will have to change your code base a lot, which is not the idea about opportunistic optimizations. But more importantly, Python actually don't have true multi-threading, because Python is using a global interpreter lock, which is a shared lock that any thread will have to get hold of to access any objects in memory. So Python really don't have true multi-threading. Python 3.13 will actually change that. It will introduce sub-interpreters and sub-interpreter locks, but until then, we don't have multi-threading actually. Multiprocessing is also a good idea, but you'll have to change your code base a lot, and you'll have to think about message passing and everything. So it's not a simple optimization that you can apply. Similarly, async IO is also a good solution if you're waiting on hardware resources or network resources. But again, it depends solely on your context, and you'll have to change things around a lot as well. I also didn't mention C API as well. You can compile some parts of your code in a low-level language like C++ and use C API. Again, the problem is you will have to compromise readability and maintainability as well. So if the stakes are high, you can do it, but it's not something that you would normally do. There might be some things that I also didn't mention, mainly might be because I don't know them, or maybe I didn't have time go through everything today. But again, the idea here is to have a mindset of opportunistic optimizations rather than going through very specific about the application of those optimizations. So to conclude, we have discussed the problem, which is that the code optimization is a balance between scarcity of system resources and scarcity of man hours. And we discussed one solution for that problem, which is opportunistic optimizations, meaning passively looking for simple improvements that you can do on your code base, which would result in significant performance improvements, at least in the context that you're working on. We discussed two traits that you need to master to apply opportunistic optimizations. First one is to have an abstract idea about the code base and performance implications that a certain decision has on the code base. And the second one is to gather a deep knowledge about the tech stack that you are working on, or at least to know where to find them when you encounter or understood a problem in your code base. Lastly, we discussed that this is not an active undertaking that you take. It's more like a mindset or habit or a routine that you would practice every day. So don't be that guy. So lastly, you might already have been doing this, especially if you are a seasoned senior engineer. But it's easy if we give this a name so we can discuss amongst ourselves and improve ourselves as well. So that's pretty much it. If you want to connect with me, you can do so via LinkedIn. I have very fresh YouTube channel as well. You can check it out. I think there's only one video there, but feel free to subscribe, and I'll hopefully get some content there as well in the future. So that's pretty much it. Thank you very much for joining.
Thank you very much, Dulaj. And for the participants, so if you have any questions, we also welcome questions over here. So as for your continuous participation, so again, I would want to thank you guys for joining our session on optimization of mere mortals. As Dulaj said, it's like not everyone likes optimization to do optimization, but everyone wants the result of optimization in their codes. So we explore the techniques to enhance code efficiency and productivity. And I commend our speaker Dulaj for his expertise. Let's remember that optimization is not an ongoing optimization is always an ongoing journey, applying what we have learned and embracing iteration. Special thanks to our Dulaj, speaker Dulaj again, and all the participants can continue to lobby, and we will have a small lunch break, and the next session will continue from 1 p.m. onwards. Thank you, guys. Thank you, Dulaj.
Thank you.
Thank you. Bye.